Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video we will start from the bending. What is bending, or what happens when bending occur in a structural beams? If we apply a load on a simply supported beam, it will deflect in downward direction, it will bend, and the top fiber will compress and the bottom fiber will elongate. So there will be elongation on one surface and the shortening on the other surface. The surface where compression occurs, the fiber will shorten, and the surface where the tension occurs, the fiber will elongate. But there is a plane at the center which is unchanged. So that plane is termed as neutral plane or neutral axis. In case of bending of beam, the plane section remain plane and perpendicular to the normal and perpendicular to the neutral axis. So we can demonstrate this with the help of a model. So here we have a beam and we have marked the neutral plane as well as the vertical section. If we bend it, so at bottom there will be compression and the fibers will be shortened, and at the top there will be tension and the fibers will be elongated, and this neutral axis will remain unchanged. And here the sections are straight, the sections are plane, there is no distortion on the section. Similarly, these sections are perpendicular to the neutral axis. So this assumption or this phenomena is used to develop the relation for stresses which are developed during the bending. Sigma is equal to my over I, flexural stress. So the normal stress on a cross section of a beam is distributed linearly, with the maximum normal stress occurring on a surface farthest from the neutral plane. So when a beam is subjected to bending, so the normal stress is perpendicular to the applied load, or we can say perpendicular to the section, will occur, and the magnitude of or the variation of these stresses is linear. So zero at the neutral axis and maximum at the extreme fiber. At the extreme fiber, at the top compression and at the bottom tension. So here it is compression and here it is tension. We can also write like this: here it is compression, forces toward the section, and here it is, and their extreme value or the highest value is at the extreme fibers. And we can calculate the stress at any location by using this relation: sigma is equal to mc or my over I. Here the c is distance from the neutral axis up to the point where we want to calculate the stress value. So here there is a demonstration of bending phenomena, how the bending occurs and how it affects the design. For the model demonstration, we have selected a stapler. So the question is how the staples of stapler are bent inside the stapler. So we apply the load over here and the needles come in contact at this position. Because of this inclined surface, when the needle comes over here and there is a pressure on the top, here act two forces, horizontal as well as vertical. Vertical force as well as horizontal force. And this vertical force initially try to bend this part of needle. And the bending will occur at the farthest point. Because of this horizontal load, the bending moment will be maximum at the farthest point. So the bending will occur at this corner. So a small, because of this horizontal force, this part of the needle will bend in this direction, and this horizontal force will disappear. Now the next bending will be because of this vertical force, and here the bending moment will be because of this eccentricity between the applied force as well as the point of rotation. When we keep on increasing the force or applying the force at the top, so this vertical force or the vertical component of the reaction will keep on bending this part of needle, and ultimately we will have this shape. So from this model we can conclude that the bending moment will be larger at the farthest point, and the failure or the bending will occur at the point where the bending moment is max. So similarly, if we see in this bench, a concrete bench, here we have a failure at this point. Although we have a higher depth at this section, but again the failure is at this point. It is because that this cantilever portion have maximum bending moment at this location. So this will be its critical point for the design. These figures show the demonstration how the concept of bending is utilized. The removal of material from the section close to neutral axis where flexural stress is less. So to resist the bending, we can remove the material near to the neutral axis. This is because the stiffness or the flexural stiffness of the member is dependent on the second moment of area, and the second moment of area will not change if we remove the material close to the neutral axis. If we keep on increasing the distance of the material from the neutral axis, the stiffness of the section will increase. Similarly, this second figure shows that we can reduce the depth of the section where the bending moment is less. At the supports here, the bending moment is 0, so we can reduce the depth, and as the bending moment keep on increasing near to the center, so we can keep the material away from the neutral axis. And on tension side, for steels, we can use the smaller section, the smaller cables, and in case of portion where the compression occur, we need a larger section to avoid the buckling as well as instability due to local buckling. So this figure shows how we can reduce the bending moment in structures. So if we can reduce the bending moment somehow, the required section, the depth of required section will be reduced. If our structure has simple supports, the maximum bending moment will be WL square by 8 at the center. But if we have a beam with fixed end, in that case the maximum bending moment will be at the support, which is WL square over 12, and at the center the moment will be WL square over 24. So just by changing the end conditions, we have reduced the middle bending moment, which is WL square over 8. We have reduced it from WL square over 8 to WL square over 24. And again the bending moment at the support, which is WL square over 12, it is less than WL square over 8. So if we change the condition from simply supported to fixed ended, the required section will reduce. We will design this, or we will decide the depth based on the reduced bending moment. If we see this figure here, these internal supports, at this internal support we have a continuous beam, so for the interior span we will consider it as a fixed ended, and as a result the bending moment will be maximum WL square over 12. But in case of this end span, if we do not provide this overhang, this exterior support will be a simple support. So because of this simple support, the moment at the center will increase. So when this moment at the center will increase, so we need to increase its depth. So to avoid that, to keep the depth same as that of the interior panel, we can change this support condition. So we can make it as continuous. We can make it as continuous by extending this beam and adding some overhangs. And we have applied this force in this direction at the end of the overhang, and this will make this internal support as a continuous beam. So by just changing the end condition, we have reduced the bending moment. As a result, the required section will be less.